So I'm not sure if people can hear me right now. So welcome everyone to our Astroparticle seminar. So this is the first hybrid seminar that we have this year. And it's also nice to have Christoph Weniger back with us, because Christoph was the last visitor that we had for all groups 2 years ago, COVID, and he had to cut his visit short that time. Now he's back, so this is a good continuation actually. So because we lost 2 years. So yeah, we are always very happy to have Christoph with us. Christoph is an associate professor at GRAPPA, which is the Center for Gravitation, Astroparticle Physics.
Yep. In Amsterdam.
In Amsterdam, so that's the last name. Okay.
Yeah.
And yeah, so Christoph is a known expert on various aspects of astroparticle physics. He has spent a long time looking for meta signals, gamma rays, and cosmic rays, and he has always been very creative in analysis methods. And today we will hear something about his work on machine learning tools and how this can be done, can be used for analysis of astroparticle. So, Christoph.
Okay, thanks a lot for the nice introduction, and welcome everybody. Yeah, it's nice to continue the visit now after 2 years and finish it. Right, so the topic of today is actually pretty much the topic of the talk that I gave 2 years ago, only now a bit updated. So we have learned a lot during the last 2 years. And what I will talk about is how to use machine learning techniques, not for dark matter searches, in a specific way where I want to focus on. This works, okay. In a specific way where we do not care that much for speed and quick and dirty analysis, but for high precision. So the question is, can we use machine learning techniques actually to replace the high precision statistical tools that we have for dark matter searches, for any kind of data analysis, and what do we actually gain from that? Good. So just one motivational slide. Most of the talk will actually be about methods. So in dark matter searches with astrophysical data, we have a lot of approaches to try to understand what the nature of dark matter particles actually is. As you all know, we know that dark matter is around, but we really don't have an idea what dark matter really is at the particle physics level. And there are many ideas of what dark matter could be. Maybe it's zero neutrinos or any more general warm dark matter candidate. This would have impact on small scale structures in the universe. It could be a weakly interactive massive particles that would efficiently self-annihilate, for instance, here in a galaxy and in a Milky Way, and maybe produce gamma ray radiation. And there are ideas that one could detect the effects of dark matter, for instance, around merging primordial black holes and things like that. These are just 3 random examples, more or less, that are related to my own research, but there are many more. But in all of these cases, the situation is typically that actually observations are already well described with the most boring dark matter models that we have, so which is cold dark matter. And so what we are interested in the end to learn more about dark matter is to perform precision observations, to understand in great detail the emission, for instance, that we see from the galactic center, to disentangle it from astrophysical emission, to understand in great detail, for instance, the stellar density along stellar streams, and see if we can see differences from cold dark matter models and so on and so forth. So it's really about precision observations rather than seeing large signals. So how can machine learning help? Well, the main or the typical motivation that you heard for machine learning in many fields is to think about or to talk about massive amounts of data. So if this is a summary plot that we prepared for some UCAPT white paper earlier.
Christoph, sorry.
Yes.
I think your slides are not moving.
Advancing, okay. But do you see actually the red dot here?
No,
probably not.
Slide 4 at the moment.
Yes. Can you move one? Maybe go back one, just in case. Yeah,
So
that's fine. Good.
does it work? Okay,
Very
great.
good. Yes, thank you.
So let's hope this works. So I'm now on slide 4. Good. So typical motivation that you hear for using machine learning is that we have to analyze massive amounts of data. And it's true that if you have trained neural network, for instance, you can pump through it massive amounts of data relatively quickly. So one of the motivations to use machine learning techniques is to be able to analyze just massive amounts of data in an efficient way. So rather than using maybe a traditional analysis technique hand-coded algorithms that you can train a neural net to replace those and be fast. But what's more interesting is, or another aspect to it, is the following. So if you ask a typical theorist, so like myself from 2009, when we predict signals from models, we try to be usually very optimistic. So we typically expect that we will see huge signals, or we hope that we would see huge signals that will be like outshining astrophysical backgrounds very clearly, so that there's actually no real question about whether we see some new physics or just astrophysics. And yeah, so just a paper from 2009 where we predicted some double gamma ray lines. So that is, if nature were nice, but actually, if you look into the history of like dark matter signal candidates, they typically are on this side here. So they are typically very weak, statistically marginally significant, and heavily affected by understanding systematics of the background and modeling, so instrumental systematics as well as astrophysical systematics. I'm not going into detail here, but what I want to emphasize is that machine learning probably can be especially useful in these kind of situations. And this is what I was mostly interested in the last years, because in most cases, when you have a signal candidate, the problem is actually to make more precise predictions, compare data and observations, data and models that you have more precisely rather than just very quick. Good. So how and in order to understand how we can make progress there, we have to go back to how we actually learn from data. And as you probably all know, there are two main schools: frequentist inference, Bayesian inference. I'm talking here exclusively about Bayesian inference, but ask me about frequentist aspects of that if you're interested. Good. In the context of Bayesian inference, we have the following ingredients. So typically, we have some parameters that describe our model and some prior knowledge for how these parameters are distributed. This can be our like physical priors, or this can depend on previous measurements and so on. So this is our prior knowledge. And then we have, if you have a new piece of data, we can try to calculate the probability of this observation Y, given the model parameters, given the specific set of model parameters. And I will give more specific examples soon. But essentially, the prior knowledge here is just the probability distribution for our parameters. The new data is this likelihood is the probability distribution for our data given the parameters, and we multiply both likelihood and prior, and obtain the posterior probability for our parameters. So that's our knowledge about the parameters after the fact, after the observation. This is just illustrated here. So if the prior would be this green line, let's say we were sure our parameter was around 20, and we have then a likelihood that actually is centered here around 25. So data prefers a value around 25, then our posterior knowledge would be this red line here. It's a bit exaggerated, but you see that the posterior knowledge will be dragged into the direction of the data. More generally, typically you have very wide priors, and then the posterior starts looking often very similar to your likelihood. So that looks extraordinarily simple, right? So you have a function, another function, you multiply both, you have the answer. The problem is usually we have not one parameter, but we have a lot of parameters. 2, 10, 100, a million. Depending on the problem, the number of parameters can be very large, and then multiplying these two functions doesn't give you much. You still don't actually understand how the posterior looks. You just multiply two functions. So in order to make any sense out of the posterior, what's typically done is to generate samples from it. So imagine, again, we have here Bayes' theorem. So the likelihood, the prior divided by some normalizing factor, the Bayesian evidence, and this here is the posterior of parameter Z given data X. Sorry for changing the variable names here. The point is this here, so it can be a very high dimensional function. In this case, it's just a 2 or 3 dimensional function. And what we typically do with it is we use some metropolis husting algorithm or other Markov chain based algorithms and generate random samples from the posterior. And once we have random samples in this very high dimensional parameter space, we can project them down to like the two parameters that you might be interested in, something like the Hubble rate and the mass of and the amount of dark matter in the universe, or the annihilation cross-section of dark matter and the mass of dark matter. And all the other parameters are kind of hidden. They are not shown in this plot because they belong to the other dimensions that you projected out. So doing this here works great. The problem is, however, that usually the number of times you have to evaluate this function here, especially the likelihood function, in order to randomly generate samples from the posterior. I'm not telling you how this is done, but I'm just telling you that it's done typically. This number increases massively if you increase the number of dimensions in your problem. So let's say this is a plot from the polychord paper. This is a specific nested sampling algorithm that is used for extracting posterior samples. Good. So what you see here is if you have just one parameter, maybe this algorithm requires you to evaluate here the likelihood, so the probability of observing X given Z, just 1,000 times. Also 10,000, between 1,000 and 10,000 times. But if you have like 10 parameters, this will be already 1,000,000 times. If you have 100 parameters, this might be 1,000,000,000 times. So very quickly, if you increase the number of parameters in your model, you end up in a situation that is pretty much unfeasible for these traditional algorithms. So you might ask, okay, why do you care about models with 100 parameters? Well, typically these parameters include, I will show you in a second, typically these parameters include everything that you are uncertain about in your analysis problem. So if you analyze data very carefully, you typically have to take into account more and more of the things you are uncertain about. And you end up typically in this regime here. You see this in this plot here. So what I do here is I take this plot and just extend it a few orders of magnitude more to the right. Oh, sorry. Good. So this blue line here corresponds to the line on the previous slide. And what I want to show is the following. So this here are now the number of parameters. It doesn't go up to 100, but let's say to 100 million. And this here is the number of simulations that you can afford to run. So let's say we are interested in some relatively simple analysis problem, like taking an energy spectrum and seeing if there's a spectral feature in it. So traditional thing would be a gamma ray line search where you fit the background with some simple smooth function and look for like a peak on top of that. This kind of model might have like 3, 4, 5 parameters. So it would sit down here. And typically making the model prediction, so calculating the data, given the parameters is rather quick. So you can easily afford running, let's say, even 100 million evaluations. So then you would sit up here, and this is what you can do with nested sampling algorithms quite easily, or probably, or many other algorithms. If you run a typical cosmological scan, on the other hand, you might have 10, 20 parameters. You want to analyze Planck data, you can afford probably to run the Planck likelihood 1 billion times, maybe 10 million times. So you're fine doing this with polychord or multinest. And basically everything in this corner here can be done with these likelihood-based techniques. However, if you look at many of the other interesting data analysis problems that we actually have, the number of parameters is actually quite large. So for instance, if you analyze the Fermi galactic center, so the gamma ray emission from the galactic center, for instance, that I showed before, so as measured by Fermi-Lat. In principle, if you're honest, there are probably about 100 or 1,000,000 uncertainties. Or just think about the following. So part of the gamma ray emission, for instance, from the galactic disk comes from how cosmic rays are distributed in the disk. It's related to where all the gas sits. So these are 3D distributions of physical quantities describing all their uncertainties. If you manage to somehow parameterize them, easily gives you 1,000,000 parameters or so, because it's volumetric data. So if you're actually honest about these uncertainties, this corresponds to huge numbers of degrees of freedom. If you analyze stellar streams, for instance, in principle, you should ideally track the precise trajectory of the stream. So stellar streams are interesting because you see the imprints of stellar streams when they collide with dark matter halos. So in principle, to describe stellar streams, you have to marginalize over all of the subhalos of dark matter in the Milky Way and their trajectories and their possible histories. So these are easily 100,000 or 1,000,000 parameters. For strong lensing images, which I will discuss later, one of the things that is uncertain is how the light actually looks in the source galaxy that is lensed. This is basically a free image, and the image, even at low resolution, you have easily 10 to the 5 parameters or 10 to the 6. So you typically have very large number of parameters. So this is completely infeasible for these traditional techniques. Nevertheless, of course, we all are able to analyze this data. And the reason is that much of the data analysis procedure is actually about finding good approximations and informative summary statistics to bring down these actually very high dimensional problems into the realm of what you can do with traditional analysis with likelihood-based inference. So for strong lensing, for instance, one would split up, one would neglect uncertainties of the source image. You can just run, assume the posterior is basically a delta function and do a map estimation. In the case of Fermi data, one would just completely ignore uncertainties in these 3D distributions that I mentioned before, and so on and so forth. In the case of stellar streams, one could assume that we're only interested in the power spectrum of the stellar stream and then Monte Carlo the power spectrum. These all are typically tricks to get us from here to here, but making these tricks often comes at a cost of introducing systematic uncertainties and effects and biases and so on. So just as an example from my own work from 2017, traditionally when analyzing gamma ray data, like shown here, so if you're interested in looking for a dark matter signal here in the center, what we have to do is to subtract all the gamma ray emission from the galactic disk, which is of astrophysical origin. And in most cases, state of the art is actually to have a physical model that predicts you the gamma ray emission, specific components of the gamma ray emission, and then combine the various physical components of this gamma ray emission, which has to do with inverse Compton emission, essentially with collisions between cosmic rays, interstellar radiation, field, and gas, and then subtract these predictions. And typically, what you are left is massive amounts of residuals. These predictions work reasonably well, but they are far from perfect. So if you just are honest, you get horribly bad fits over the entire sky. So these are, I think, in units of sigma deviation. So you have here easily 20 sigma excesses, 20 sigma like negative excesses, and so on and so forth. And that's kind of standard, and everybody is used to that. And then one tries basically to distinguish here excesses that you believe in from excesses that you attribute to systematic uncertainties. That's a very simplified summary of the situation, but neglecting uncertainties in the various emission components leads to large residuals. That's the bottom line. And we introduced in 2017 an approach that allows to take into account more uncertainties by basically parameterizing them away. And instead of having a model with, let's say, 10 parameters, we had here a model with 10 to the 5 parameters. But this is still a likelihood-based approach. So it helped us to reduce residuals massively, but also doing this in practice turned out to be a massive headache. So we wrote nice papers with this, but it doesn't scale to many other problems. But okay, so that's the situation. One thing that I wanted to say. So one massive problem with likelihood-based techniques where you deal directly with all these parameters is that even if you're only interested in one parameter or two, like the annihilation cross-section of dark matter or the mass of dark matter, you are necessarily, or you are forced to understand all of those parameters. You need to get each and every of your million parameters right in order to get a good fit to the data. So even if you want only to extract information about a handful of parameters, you have to understand all parameters and the correlations between all parameters and your parameters interest and all correlations among them. So usually you're in the process of getting simple answers for single parameters, you have to do a massive detour through this super high dimensional problem. Is this advanced? No. Okay, but I have to go to the next slide. Maybe this switched. Yeah, maybe I did this. I don't know. Okay, good. But let's do a little thought experiment, which looks like impossible to do from the perspective of likelihood-based inference. So look at these images here. Okay, these are just random images that I took, I think, from unsplash.com or whatever. Good. So assume these are random background images, and you see that there is this yellow moon that has different positions, obviously. In all these images, right? And now assume we have a parametric model for these backgrounds. So we have some magical model that predicts, for instance, a forest and the position of each tree and the position of each leaf and so on. Or alternatively, like a boat and the water and the weather and the color of the boat, right? So you could imagine you have like a super master model that predicts all possible images basically on Google. It has probably 1 million parameters, I don't know. It's very high dimensional, certainly. And one of those parameters is the one that you actually care about, which is this parameter of interest, which I made here red. And you know which parameter you're interested in because you wrote the model. And you know, hey, I'm interested in parameter 1. In the fourth parameter in this like 1 million parameter list. So now you can like just look at these images here, right? These are 9 images or so, and look at the number. And then it will not be very hard for you to predict what that red number will be once you see this new piece of image, right? So stare at this for like 5 seconds. And I mean, it's just like complete the sequence, right? So you will probably have guessed that that number is maybe around 8 or 9, right? Because this parameter simply parameterizes where the moon is from left to right. So your kind of brain as a neural net has required maybe 5 or 10 training examples to be able to interpret this new image. You still don't have any clue what all these other parameters are actually, right? But you also don't care. So the beauty of this is that you actually manage to like shortcut the problem of likelihood, or a problem that would have been impossible with likelihood-based inference. In likelihood-based inference, you would have ended up not only with this number, which you wanted to know, but also with all the other numbers of the model. And obviously you don't care, right? It's nice to have them, but you don't need them. So you managed to train your neural network, and I mean, your head, whatever. I mean, you figured probably this mapping out from like this observation onto that parameters, because you essentially learned how to recognize the relevant patterns in the image, obviously. And it's rather simulation efficient in the sense that you didn't have to like run your simulator or your likelihood 1 million or 1 billion times, but in this case here, like 8 times, right? So how can we make use of? But one caveat is, of course, this is kind of quick and dirty, right? This falls into the category of quick and dirty. So is this moon here actually at position 8.13 or 8.14, right? That would be hard, and that's nothing our brain can do easily. So how can we do this with neural nets and still keep precision? Well, I come in a second to that. So first, what this lets you do in principle is to do the following. So imagine we had some analysis techniques that were based on the same concepts. And then we would be suddenly able to analyze also models which had a bazillion of degrees of freedom, as long as we're only interested in a few of them. So in principle, and this approach is called simulation-based inference. So in principle, what this allows to do, if you could set this up correctly, is to look at models not only in this like triangle, left upper triangle, but everywhere above this line. Where this line exactly sits, I don't know. It depends on the scenario. But typically 1,000 or 10,000 simulations are enough to get started. So it's possible to look at things like the galactic center excess or stellar streams or strong lensing images, taking into account all uncertainties with these techniques. And I will now tell you a bit how those techniques actually work. So no, before I will give you an example for the cosmic microwave background. I mean, this was just like abstract, right? So cosmic microwave background, that's typically something that you wouldn't analyze with simulation-based inference, because we all can do this with like with the public Planck likelihood codes and with MCMC, with nested sampling, polychord, dynasty, and so on. But still, it's interesting to see what you actually gain by doing it with simulation-based inference. So what's the data? Well, data would be here, the measured CMB by Planck, and then we look at, for instance, temperature, angular, the angular power spectrum of temperature fluctuations. And what you're interested in is now actually simulated data. So rather than just calculating the likelihood of the observed data given, model parameters, we are interested in a simulator that simulates lots of possible data realizations with noise given different experimental parameters, right? So we are interested in having examples that look basically like this here. So, example spectra and then the labels that we are interested in. So the cosmological parameters. Good, so we can do this and then use those simulations to train a neural net and use that neural net to predict posteriors. And what we find is that, so this is some recent, I removed the reference. This is a recent paper with a postdoc at GRAPPA, Alex Cole and collaborators. So you find this on arXiv. So you see that with just a few thousand simulator runs, we are able to reproduce the posteriors that you would otherwise get from MCMC, in this case here with like 1 million or so simulations. And the fun thing, I think I switched something off again. Yeah, I think this, okay, this works, yeah, thanks. So the interesting thing is you see here posteriors only for 6 parameters, for 6 cosmological parameters. These are the parameters that the neural network actually saw. The neural network never saw these other nuisance parameters here, 13 or so. So they are corresponding to the parameters we are not interested in. Those were never actually shown to any neural net. They are still part of like describing how the data varies, but they are not part of the analysis problem. So in principle, we could have had also 1,000 nuisance parameters, and this wouldn't have increased the costs for getting these posteriors. Whereas if you try to do the same thing with a likelihood-based approach with Markov Chain Monte Carlos, you need to like look at all of those parameters and get posteriors for all of those parameters. So here we only have 2-dimensional posteriors, right? 1-dimensional and 2-dimensional ones. The MCMC would have had to generate 16 or 20 or whatever dimensional posteriors, and then we would have downsampled this. This is why it requires so much more samples, actually. So how does this work? Well, it's based on what's called, so this research field is called neural simulation-based inference, or simulation-based inference in general. And it's very actively in development. So you can, for instance, look at the paper, which is now, again, a bit outdated, of course, from 2019, which compares a lot of approaches there. There are a very large number of approaches to perform this. Okay, the general goal is to approximate with these techniques posteriors, like this here, or sometimes likelihood functions, like this here, or sometimes density ratios, like this here. So the obvious thing would be to write a neural network and then somehow find a magic way to directly approximate like posteriors, like they are shown here. I'm not telling you how this could be done, but I mean, one could imagine, okay, you define a network which somehow describes this posterior here and then find a magic way to train that posterior. The problem with this approach in general is that in order to describe probability distributions, you need to describe functions that are non-negative and that are normalized to 1. Otherwise, it's not a probability distribution. There's an entire research field behind this, which is related to normalizing flows, which allows you to have neural networks parameterizing these probability distributions, but they tend to be not completely trivial to train for various reasons. And there's lots of technicalities behind this. Then there are likelihoods. So you could instead try to replace very complicated likelihoods by low-dimensional effective likelihoods, which only are likelihoods like for the few parameters, for your data, given the few parameters you're interested in. That has the same problem. In some sense, you need to normalize your likelihood function to 1. So you need specific network architecture for this. What turns out to be rather simple actually to do is instead focusing on ratios that look like this here. So ratios between probability distributions, and I will show you more of this in a second. They are not normalized to 1. You can just use any network that produces numbers larger than 0. And they tend to be much easier to train, at least in practice, at least for us. This worked much better usually. So I will tell you more about this approach here and how to do this in practice and how it actually works. In order for that, it's useful to look at this cat and donkey example. So what do these factors here actually mean? Well, this here is your prior for parameter z. This here is essentially the I have this probably somewhere. All right, sorry, I should have had this earlier. This here is the joint distribution between data and parameters. So you can think of it as like prior times the likelihood function. And here the ratio, and this is then divided by the probability of the data given your model, so Bayesian evidence and the prior. And then you can simply essentially use the definition of conditional probability distribution and convince yourself that this is the same as the posterior divided by the prior. So by learning this kind of ratio here, we directly learn the posterior divided by the prior. If you don't believe me, just look up how probability distributions work again. But what I want to show you now is how this can be done with in the specific example. So imagine this first thing here draws random labels or random parameters from your prior, like cat or donkey. And then this second function here draws random images. So it's a probability distribution of random images that either show cats or donkeys with a 50-50 probability distribution. And then imagine that there is yet another probability distribution, this joint distribution, which randomly draws matching label and image pairs. So if you randomly draw from this thing, you will get a label cat with the cat image and a label donkey with donkey images. And then you can define yet another thing that that draws random labels and unrelated random images. So sometimes you end up randomly with some matching pairs, and sometimes you end up with randomly with non-matching pairs, right? Okay, so then this here would be jointly drawn parameters, and this here would be marginally drawn parameters. And that's that. And then you can ask the very simple question, given some pair, so let's say this pair here of a label and an image, what's the probability that it was drawn from this distribution versus the probability that it was drawn from this distribution? Right? So you can ask, okay, if this is matching, what's the probability that it was drawn from this versus this? So what's the yeah, and that's the game. And this is a simple, this is in some sense a simple hypothesis testing problem, a binary classification problem, because given some input pair of parameters and data, we just have to decide, okay, do they belong to each other or are they random and uncorrelated? And so you can call H0 the they belong together category, and H1 the they don't belong together category. H0 would be jointly drawn, H1 would be marginally drawn. And then if you manage to estimate that probability, you actually estimated this ratio. This here is just the odds ratio of jointly drawn versus marginally drawn. And that's it. So the entire problem of estimating Bayesian posteriors boils down to this very simple binary classification problem, which happens to be like the simplest problem you typically can deal with in machine learning in many ways. So how is this done in practice? Well, several ways to do it. The simplest is probably the following. So imagine you have it's called a very flexible function approximator, which happens to be a neural net, which takes as input your image and your labels and spits out a number between 0 and 1, which you interpret as probability. And this thing has like lots of maybe 1 million degrees of freedom phi, which are the network parameters. And then you train the network such that if you plug in some parameters and models that match, data that matches, that it returns 1, and otherwise it returns something close to 0. Question is, how do you actually get to this function? It turns out to be, again, very simple in some sense. So you might forget about this being a neural network. Just consider this as a very high-dimensional function that lives in data space and parameter space and projects this down to a single number. Yeah. Then you can, in principle, write down a functional of that function, which happens to be our loss function. But think of this now as functional, which is probably more appealing if you're a theorist. So think of this as a functional of this high-dimensional function. What you can then do is we can just write down this this expression, which happens to be called binary cross entropy, where we have here a factor of the joint distribution, here a factor of the marginal distribution, and then you can convince yourself that if you minimize this here, you can show this with functional derivatives. If you minimize this function, then this function d here becomes simply the ratio between jointly drawn parameters and jointly plus marginally drawn parameters. And you can use simple algebra to get from this back to this expression here. And then since you know the prior, you know the posterior. And in practice, of course, like minimizing arbitrary function and minimizing this by minimizing explicitly here, this maybe million-dimensional integral wouldn't work very well. But if you replace this function here by a neural net and minimize the loss function by using stochastic gradient descent, it works pretty well in many cases. And you often end up very quickly with a good approximation to the posterior. And I'm not going into details about how to train neural nets, but essentially there is where the magic comes in then. But there are good mathematical reasons why you expect to get actually the correct posterior out of that and not anything else. Good. So one beautiful thing is now that we can cherry pick whatever posteriors we care about and forget about the rest. So one way we, for instance, implement this is the following. Imagine we have this like 100,000 parameters or whatever. And then we have some data, which might be an image. And then we have maybe a convolutional neural net that like extracts a few features from that image. Then we can just concatenate whatever like parameters we're interested in together with those features and train a flexible neural net to act as posterior. And so we can do this then individually for instance, the first parameter or the second parameter or the third and the fourth parameters jointly. And in this way, what we end up with is a posterior for the marginal posterior just for the first parameter, marginal one-dimensional posterior just for the second parameter, then a two-dimensional marginal posterior just for the third and fourth parameter, but we did not waste time in estimating the correlation between the first two parameters or the first, two, second, and third, and so on and so forth. So you can target whatever you want and forget about the rest. But can we actually trust results, right? So,
Christoph?
Yes.
Sorry to interrupt. Jason has a question. So Jason, you can unmute yourself.
Yeah. Hi, Christoph. Can you hear me?
Yes. Yeah.
I have a question. If you go at this slide, is it a requirement that theta 1, theta 2, and theta 3, 4, that conditional probability, do they have to be nested for this to work? Because to use the natural logs and the cross-binary entropy generally requires nested hypotheses. Is that a requirement here as well or not?
No, that's completely independent. You can also use this for discrete parameters and discrete hypotheses and so on. But I mean, it's not related to nestedness of hypothesis. Which you,
okay, thank you.
Okay, so one question is, can we trust results, right? So if you play it with MCMC approaches, you kind of get an intuition for when things work and when not. But this year is in the end a black box neural net. So why should you ever trust a neural net to tell you that you discovered new physics, right? So one beautiful thing again about this year is once the network is trained, what happens here? Sorry. I think when I press too many buttons too quickly, strange things happen. Good. So one beautiful thing is once this year is trained, you can evaluate super quickly. So in contrast to MCMC algorithm, which you run for a month and then you have one result and then you're living with that. Here you can just, once the network is trained, evaluate it on many, many mock examples and see how it performs and then learn to trust it or not to trust it, given that you have a trained neural net. And one thing one can, for instance, do in that case is to look at the expected Bayesian coverage. So since it's Bayesian inference, no free, yeah.
So when you talk about trading, is the trading done with MCMC results or some other?
Say it again.
When the training is done.
No, the training is done with random draws from the prior. I will come to that in a second. So you randomly generate draws of your parameters from the prior, calculate simulated signals that belong to that draws, and then you train with this. And then the network in this context here learns to predict all possible posteriors at once. So once the network is trained, you essentially trained this ratio here, right? But for all possible images. So afterwards, you plug simply in whatever image you measured, and you look at the posterior. Or you plug in another image, and you get immediately the other posterior. So it's kind of an inference machine that you trained. This makes it possible to look at the following thing. So what we would expect in the Bayesian context is if we do the following things. So we sample from the prior, then we generate a piece of mock data, then we calculate the posterior of for that mock data. And then we check whether the true parameter that we initially sampled actually falls into the 68 or 95 credible contour. However we defined our credible contour, it doesn't matter. Then we expect that this happens in 68 or 95 and so on and so on of the cases. That's a bit a weaker statement than the frequency coverage statement, because there the statement would have to be true for all without averaging over random draws from the prior. But in the case of Bayesian inference, this is what we still would expect. And we, oh, sorry. And we can simply make this test. So we can then simply take some simulated data and check how often the true value actually lies in the credible contours, and make plots like this here. So we can then see, okay, for the examples that I showed before, our cosmology examples, for instance, the 68% credible contour contains the true value in 70% of the cases. So that's good. That's on the conservative side. You are not overconfident, and so on and so forth. And what typically happens is if you like don't train your network fully, then the network tends to be even more conservative. So your credible contours contain the true value even more often than they claim they do. So that's a way to test this. That one could say much more about this, but one can essentially do then afterwards these plots. So you can then for each and every posterior that you care about, check whether they actually have proper statistical properties. And if they don't, then you can even correct for them. So there's nothing that stops you. Yep.
Which means in the next part, this is actually a way of testing if it learned that parameter in particular well.
No, it's a test that tells you that it learned any parameters in this plot here well. So it's averaged over all parameters in this plot here. It's an average statement. It doesn't tell you whether it learned that particular parameter well, but it's an average statement that it in general learned all parameters well. There are caveats to this. But I mean, if you are really a diehard frequentist, just a second, if you're a diehard frequentist, you can even, and what you want there is not coverage like on average, but you want to have coverage in each point, right, of the parameter space, because you have no idea where your truth lies. You can use the same approach to just calibrate your confidence intervals using Nyman belt construction or whatever, and that's very efficient still in this context. Then you have proper frequentist intervals. Yeah. You had a question? Sorry. Yeah, no, but you had a question.
So, my question is that, so for MTS, we can 100,000
yeah.
But are all possible shapes that we can get from MTS, can we put in all possible shapes with all
Yes, in principle, yes. I mean, again, that's in principle, right? But here the things are Gaussian just because we use the cosmology example. But you can have also like multiple modes. So for instance, in one of the slides that I don't have here in the talk is we looked at, there's this egg box example that people like to use for MCMC samplers. So imagine you have a 10-dimensional problem, and in each direction you have 2 modes. Then you have like 1024 modes. Sampling this with MCMC requires you to have like samples in all the 1000 modes, which requires a lot of simulations, right? And if you go to 20 dimensions, you have like 1,000,000 modes. So this becomes less and less fun. But the point is you can then learn directly 2-dimensional posteriors or one, and you get the modes and you get whatever shape you want. I think the point, I mean, that's a very good question. I was thinking about this a lot.
Sorry, Christoph, sorry, could you repeat the last question by Shashank?
Yeah, the question was, there's no free lunch. So how the hell can this actually work, right? Because it looks a bit like magic that you can get more results, namely inference machine that works for all kinds of observations with less simulations. That's kind of so. I found this also initially very counterintuitive and confusing, but in some sense, if you think about a likelihood-based approach, what you do there is in some sense extremely inefficient. You run a simulation, right, which gives you maybe a beautiful image, right, with all details. And then the only thing that you do is you take that entire image and like squash it with the data down to a single number, which happens to be your likelihood. And then you try to figure out everything from that single number. And that number is affected by the parameters you care about and everything else. So in order to learn anything from that number, you have to very carefully average out all the parameters you don't care about until you see how this one number is affected by the parameter you care about. So that's very efficient. Here to think about this, it's more useful to think about ABC, traditional approximate Bayesian computation. So where you typically try to figure out a summary statistic for the one thing that you care about, and afterwards build posteriors based on that. So it works very much like this. This thing.
At some point, the spectral decomposition and the physical coefficient, assuming that you know at the back of your mind that the spectra are very smooth.
You can build, you can build information like this into the structure of the neural net if you want, but you don't have to. This goes into neural network design in some sense. Yeah. I can show you more examples after. They are as general as you want, given that you can make neural networks as complex as you want. So there is no inherent limitation to this approach. Yes, I can give you more examples where it becomes more. So let me see how much time I have left. Yeah, so I mean, one difficulty is to get very precise answers, for instance, because if you train a neural net to predict you all posteriors over a very wide prior range, then again, you do too much. You actually care about the posterior for a specific parameter, right? And the way we handle this, again, that's an open research area. We proposed a new algorithm that works as follows. So we initially sample from the full prior. We use simulation data from the full prior to simulate some posterior that happens then typically to be too wide. Then we use this too wide posterior to exclude regions of the parameter space that certainly are not consistent with the data. Then we define kind of a truncated prior, simulate more in this region, and get more narrow posteriors until it converges. This works pretty well. For instance, here in the cosmology example, we start with these very wide priors, and then we use them to get some initial posteriors that look like really horrible and wide. This is shown here in blue, and then this helps us nevertheless to exclude regions of the parameter space and simulate more data in the regions which matter. And this can be done in various ways. So one can, for instance, zoom in. Like it's a bit like multi-nest would maybe work, so nested sampling. So you can zoom into the relevant part of the parameter space and generate posteriors there. So that works pretty well. And right, then in this context, we proposed this algorithm that we call truncated marginal neural ratio estimation, because it's using neural ratio estimation, focusing on marginal posteriors rather than the full joint, and allowing this truncation scheme to zoom into the relevant region of the parameter space. And I could say much more about this, but I want to, right, and then we have a software library that implements this, which is under heavy development and that we use for all kinds of analysis problems. So if you're interested in this, I recommend you to have a look. Called it Swift. Good, Swift, whatever. Good, strong lensing. That's the example I wanted to get to. Do I have 5 more minutes? Yeah. Okay. Good. So now let me show you a non-trivial example. I mean, the CMB is like a bit under complex in that regard, because also we have actually analysis approaches that work there anyway. So let me talk about strong lensing. Well, strong lensing, let me just jump to this plot here. So what is strong lensing? Well, most of you will have heard about it. So the idea is, let's say we have like a distant source galaxy at redshift 1 or something like this, and then another galaxy that happens to be on the line of sight between us and that source galaxy and that original source galaxy. Then what happens is that the mass of this lens galaxy, including like baryonic and dark mass, will lens the background galaxy if they are nicely aligned, typically into something that looks like this ring here, or like a bit like a ring. And you will essentially see the same source galaxy multiple times, 2 times, 4 times, or even like a perfect ring. So good. So okay. So far, so good. So what you can then learn from the ring itself is, for instance, something like the amount of mass in the lens galaxy. That itself is not super interesting necessarily. But what's interesting is now that if there are subhalos, and there are subhalos, but subhalos along the line of sight, or small halos along the line of sight, or subhalos in this main lens, will very subtly affect this image here. Typically, these are tiny perturbations at the percent level. So the smooth overall halo or mass distribution of this lens galaxy will determine how the image looks in general. And then subhalos will act as like very localized distortions of this simple, relatively simple lensing effect, and lead then to tiny, yeah, as I said, tiny distortions in the image. And the idea is now to use these very tiny distortions to study substructure of dark matter in strong lensing images. That's a well-known probe nowadays for dark matter substructure, has led to detection of several subhalos already. Whether it's the best way to look for substructures is a bit unclear, but it seems to be certainly the most challenging one. It's a really hard statistics problem. And the reason why it's a really hard statistics problem is that the source galaxy typically doesn't look like a nice blob, but it's like a real galaxy with real complexity. The lens galaxy first has its own like galaxy that shines, and then you have a dark matter halo that isn't necessarily just a nice profile, but something that might have complexity itself. And then you don't obviously know where the subhalos are and how many and how massive, right? So it's a problem where you have easily 10 to the 5, 10 to the 6 parameters. You have reasonably good priors for all of these things, right? From n-body simulations and from like images of galaxies. But it's very hard to actually analyze this because you have to deal with these large number of degrees of freedom. Right, at this point, I wanted to click on this link and open a website. I don't know if this works. Yeah, nice, okay.
Can you still see this on Zoom? Probably not.
No, it's still on the slide.
Okay, sorry. Yeah, sorry. Yeah, so that's nice. I mean, animation that Alan Coogan, one of my previous postdocs, wrote. You see there, that's like the source galaxy. This is the lens galaxy. The massive thing in the middle is the lens light, so we can turn this off. And then we can switch on like ELT resolution. Then you see like this lensed image here. And one can play a bit with like the source position, and you see how the thing moves, right? So that's the lensed image. Now, if you resample okay, now I show the subhalos. No, yeah. This here resamples where the subhalos are, and you see probably each time that the image changes very, very slightly. I can also show you the subhalos in this simulation here. So this is where the subhalos sit. So this kind of tiny variations are the things that we are interested in, and we are not only interested in like detecting these variations, but seeing where they stop. So we want to know, okay, there are certainly large halos, but then at some point, if we have warm dark matter, there will not be halos smaller than 10 to the 7 solar masses, or 10 to the 8, or 10 to the 6. And we basically want to detect the absence of the tiniest of those halos. So that's a kind of very difficult, somewhat crazy problem to solve. Can I go back to the slides? Sorry. I thought these animations are nice because they illustrate better what's going on than the standing picture. Not Safari, I think probably this. This. Okay, so that's the thing. So in reality, the problem is that lensing images all look different, right? So first you have the source somewhere, so the source galaxy lensed in this background, and then there is the other, I mean, the lens galaxy in front of it. They all look completely different from each other, and still we are looking for these like 1% variations in the image. So that's a very hard task, and it's hard to imagine that you can train a neural net to be able to deal with all of these images simultaneously, right? Because you are looking for so tiny effects in these very, very different images. So training data variance would be much larger than the signal that you look for. So what you're interested in, as I said, is to essentially use then these images to learn a single parameter, namely the cutoff of the subhalo mass function, let's say. So depending on the mass of dark matter and warm dark matter models, there wouldn't be, let's say, subhalos below 10 to the 8 or 10 to the 7 solar masses. So we are interested in simulating models which have subhalos down to a specific scale, and then train a network to tell us whether, given a set of images, what's actually the posterior for this cutoff scale. And so the way we ended up doing this is the following. That's still work in progress. So what we do is essentially a two-step process. And it's similar to what I mentioned before. So initially we start with the full prior range of our model. And in this case, we use here a Gaussian process to describe the source galaxy. And then we fit the galaxy using something called variational inference, which I haven't mentioned much. That's yet another fancy machine learning technique. So we fit images with variational inference. These are like mock images. This would be a fit. And this is the original source. And this here would be the reconstructed source after the fit. So you see, we can reconstruct even very funny looking source galaxies reasonably well. This here are the posteriors, sorry, the residuals. And then what we have is essentially, we zoomed into the relevant region of the parameter space, and we can now use our fitted posteriors to define these truncated priors that I mentioned earlier, right? So we remove essentially everything from the parameter space that doesn't look like a given image. And then for this given image, we can generate training data for a neural net to tell us something about substructure. And then this neural net doesn't work for any image anymore. It only works for like the one image it's targeted at, but it solves then the statistics problem that we want to solve for that particular image. So just an example, I don't have tons of examples for this yet. So this here would be, for instance, a random piece of training data that was generated for an image that happens to look like this here. So lensed galaxy into this Einstein ring-like structure. And one can then, with many images that essentially look like this and almost only differ in where the substructure sits and a bit in how the galaxy looks and a bit how the main lens looks, we can then train a neural net to give us posteriors for here in this case, the cutoff scale of the subhalo mass function. And you see actually so the truth was here, this line, this cutoff scale goes between 10 to the 7 and 10 to the 9.5 solar masses. And you see the posterior isn't very impressive, right? It looks kind of like the prior. And the problem is simply that even if you solve the statistics problem correctly, you're still have to live with the fact that there are only a few handful of subhalos in this image. And most of these subhalos wouldn't have any noticeable effect on the image, only the ones that happen to, the few ones that happen to intersect actually with like bright parts of the image will matter. So essentially you try to get population properties based on 3 objects here. Obviously this doesn't give you strong constraints. So what one has to do in the end is to combine many images. And on paper this still works, you know, it's in practice this starts working. I don't have tons of results to show for this yet, but there should be a paper in a month or 2 on this. So the point is we can combine a larger number of images with posteriors that look like this here and aggregate the statistical power of all these images and end up with posteriors that look like this. So this here is a posterior based on, for instance, 20 mock images that we combine. There are challenges related to this. One of the challenges is to that the posteriors start to become typically biased and complicated. So if you run these checks that I earlier showed with the diagonal lines, right? So for the coverage, they start to look less and less nice if you combine 20 images with neural nets that were trained on individual images. And one of the reasons is that the approximation errors that you make for the posteriors just accumulate if you combine many of them. So what we ended up doing is to use then a Nyman belt construction to get, again, proper confidence intervals in that case. So that's still work in progress, but it starts working. And so these techniques allow us here in this case to analyze essentially images with or models which have formally 10 to the 5 or so parameters and do this in a statistically sound way. And yeah, so that's what I wanted to say. So conclusions are there are petabytes of upcoming astrophysical data that have the potential to provide key information for dark matter. The particular matter in the universe. There are many fronts. The ones that I mentioned were strong lensing, image analysis, gamma ray searches for dark matter. Also, stellar streams are interesting, gravitational waves, analysis of X-ray data, analysis of radio data for like axion photon conversion, neutron stars, and so on and so forth. What many of these areas have in common is that in order to actually find dark matter signals and like be more or less convinced about what we see, we have to be very sure, we have to be very accurate with our models and very honest with the things that we don't know in models, which typically introduces more uncertainties. And dealing with those uncertainties and unknowns is very hard with existing analysis techniques. And what neural networks can do is to shortcut this problem by giving you directly answers for the parameters you care about. There's still a lot of work to do to actually figure out strategies to get the most precise answers, to get unbiased answers, to get like robust answers. But I think there's quite a bit of progress during the last years. And yeah, there's certainly much more to come. So from my perspective, this is really a paradigm shift in how data analysis works. Much of the pain of what I did during the last 10 years, looking for like dark matter signals in gamma ray data and so on, would have been much less painful with these approaches. But it's still like in very early days, so one has to learn how to use them actually. That's it. Thanks.
Questions, so if there are questions on Zoom, I think Maurice was going to monitor questions in hands raised. We cannot see this here on the topic. Questions from the audience?
Yeah, so we tried two things. So one is just convolutional neural nets, and they work surprisingly well on all kinds of problems, but are not always the best solution. So for this year, we found this works reasonably well if you have enough training data. What we found works a bit better is if you do kind of matched filtering. So we had kind of we played around with a custom layer for pre-processing data in a specific way so that it's that's easier to extract lensing signals. This typically reduces the amount of training data that one needs. So that helps. But let me add to that point. So one problem that is very hard to solve with a convolutional net is the following. So imagine we want to analyze the CMB, right? And the only thing we would care about is the normalization of the CMB. Let's say we have then 1,000 bins. To get like a good estimator for the normalization, the only thing that we have to do is to calculate like the average of all the values that we have in some sense, right? And that's a very simple process on paper. You just sum everything and divide it through the number of bins. And that's the best that you can do if you have Gaussian noise and so on. So if you have, I mean, depending on the noise, but this can be the best thing that you can do. And it's very simple to do this, like mathematically, it's very simple to arrive at the conclusion that that's the best thing to do. But for a like super complex neural net to learn that rather than doing highly complex nonlinear transformations, the only thing that it has to do is like summing things is very hard. So usually when you train a neural net like the CNN to analyze things like the CMB, you end up with posteriors that look nice, but that are never as like accurate as the one that you would get from MCMC. Simply because these structures are more complex than what the flexibility of those structures introduce a lot of noise if you look at simple problems. So what we, for instance, did for the CMB was something very simple. So I have here this, I mentioned here this embedding thing, right? So what the embedding looks for them CMB is simply a linear transformation from like all the bins, I think 2,000 bins or so, down to 10. So it kind of learns a simple linear, it's like a bit like a principal component analysis of the CMB. And that turns out to work very well for this kind of problem. So bottom line is a bit, since we have to analyze, since we analyze data, right? It's simulation-based inference, not likelihood-based inference. One has to be very careful with what kind of networks you use and what kind of structures. And of course, there has been a lot of research in network design, but most of the existing standard approaches don't focus on like super noisy data, but focus on like highly complex data. Often the data we deal with is actually pretty relatively simple and riddled with noise, and focusing on like good network structures that deal with that is like certainly something that requires more thought. Yeah, maybe this answers part of your question.
Are there any questions on Zoom? Maybe ask one more practical question. So this showed there what kind of
which simulation do you mean?
so basically what you showed there at the last point.
The strong lensing thing?
The strong lensing, they basically derived
that actually these kind of things require far less computational resources than like traditional lensing pipelines. So usually, I mean, running like 10,000 simulations requires maybe an hour, but on a single GPU. And then doing the fit typically requires another hour. So it's like really fast compared to like, yeah, it's really fast. And not much. If you start scaling this up to like, let's say hundreds of images at some point, then this will require also large computational resources. And also doing high resolution images will require more, but it's manageable, I would say. The training time is typically an hour or something. I mean, or 2 hours, a few hours at most. You get reasonable results typically after a couple of minutes already.
Let's assume I want to do this by some that map that lines the gamma ray how well the neural network work if my background model with I mean how strongly I was physical uncertainty that will affect any. I mean there are physical aspects such as cosmic ray diffusion that we still have not understanding. Is there any book or neural network that will help us?
I think for most of these problems, actually, the question is not so much on the neural network side, right? So the neural nets, given simulation-based inference, what you can basically do is you can assume that you can solve any possible Bayesian inference problem, and then leave that aside. And then if you're in the situation where you can solve any Bayesian inference problem, the problem is actually to define the model first. And that's, I think, the challenge. So in the case of coming up with good, so typically what you would do, for instance, in a line search, right? In gamma ray data, you don't even care about defining a good physical model. You assume that whatever the physical model is, the background will be smooth and the line is a peak, right? And this gives you this might give you good answers in many cases. But let's say you look for gamma ray lines that, or whatever, for more complex signals, right? Where you wouldn't know how to reduce it like this. Where do I want to get with this? Then what neural nets essentially allow you, how to say, let me come back to this model argument. So the problem is then really, if you have GRAPPA predictions, right? They will not give you all the uncertainties even if you want it. So for instance, you have uncertainties in the gas distribution, uncertainties, actually cosmic rays are like 3D distributed, not like radial symmetric. There might be stochasticity, right? So burst events and things. So not everything is steady state and so on. So this is quite endless. And in order to really exploit all information from gamma ray data, what you would have to do is to come up with a model that incorporates these informations, these uncertainties. And in some sense, I think the fact that the nice thing is now that in principle, if you use simulation-based inference, it doesn't cost you extra to actually include these uncertainties. For instance, in case of GALPROP, let's imagine your gas model is uncertain, right? If you wanted to deal with that uncertainty in a likelihood-based way, you would have to have like basically a model that describes with a very large number of parameters how the gas density varies around the mean values that you measured in some way from CO maps and stuff like that, right? And you would have to fit this very high-dimensional model to the data. In a simulation-based approach, what you essentially have to do is you simulate variations of your gas models around the mean that correspond somehow to your measurement uncertainties, and include this in training the neural net. And in this way, you automatically marginalize them out. So the main problem is that in this kind of game is that I think people up to now haven't really bothered often to quantify their uncertainties. So that it's not that you can download somewhere how uncertain are gas maps or how uncertain are interstellar radiation field maps, right? It's always assuming one number, assuming one mean value, and then you have to deal with it. So I think it's not the neural networks part which is the problem, but it's the problem that we have to actually deal with our uncertainties and be honest about them. So if there's no information about uncertainties, also these fancy analysis tools will not help you anymore at all. But one more thing about this. So for instance, GRAPPA simulations in 3D with like randomly drawn sources, this is extremely time consuming, right? Which is part of the reason why you would never dream to do this like an MC-based approach. But if you only, let's say, need 10,000 random realizations of those, right? And you can maybe deal with data augmentation and like boil this down to 1,000 simulations, it could be actually possible to even run very realistic GRAPPA simulations in 3D and use them in a real analysis. So these are advantages that in principle are there, but yeah, one has to sometimes often completely rethink how one sets up the entire problem in the first place to really exploit what one can do with simulation-based fields. But that's kind of part of the fun.
One last question.
Yeah. Yeah, I'm still trying to. So are you talking? Yes. You are talking about how these images are affected by subhalos, or? Yeah. Yeah. I don't think there's a double counting in that sense. I mean, the simulation itself is just forward modeling. Are you talking about the initial fit and then simulating? Okay. Okay, good. Yeah, that's a good question. So the question is about this two-step process where we first fit the image and then afterwards generate training data for a neural net. So in this first part, of course, we somehow have to deal with subhalos, because if you would just leave them out of the fit, we would neglect a good fraction of the mass in the system and get very wrong results. So what we do there is during the fit randomly sample subhalos, which then are kind of averaged during the fitting procedure. For technical reasons, because it's variation inference, it kind of gives you two narrow posteriors in the end, but we just like blow them up by hand right now. In the near future, what we plan to do is to build everything just on neural ratio estimation without variation and inference. And in that case, everything is kind of consistent. So in the initial stages, you would marginalize out subhalos automatically. And then after a while, you would become sensitive to them. Yeah.
Okay, I would suggest we should release Christoph. But before we do this, let's thank him again.
Thanks. End of next week, yeah.
And he's located in office C12. So this is one of the offices opposite to the library. It's a little hidden.
Thanks.